E and Z geometry isn't just about same side and opposite side. It's about priorities. And once you see that, this topic stops feeling like an educated guess. Hey there, ninjas. This video is about one thing: how to assign E and Z labels correctly and consistently. No memorization, no guessing. If you can follow a short checklist, you can do every exam problem your instructor throws at you. With sp3 hybridized carbon-based chiral centers, we used R and S nomenclature. With alkenes, we use E and Z. And the logic is similar, but it's applied separately to each carbon of the double bond. E and Z only applies to alkenes, and E and Z can apply to any alkene, even when cis and trans labels fail. With 3 substituents around this tri-substituted alkene, we couldn't really name this cis or trans. What is cis to what, and what is trans to what? And that's why E and Z is the official IUPAC naming system for alkenes. The abbreviations E and Z are derived from German words. E stands for entgegen, which means opposite, and Z comes from the German word zusammen, which means together, or as I like to call it, Zee Zame Zide. But what are we referring to when we say together or opposite? We're referring to the number 1 highest priority group separately on each of the 2 alkene carbons. Let me walk you through the checklist. Step 1 is always the same. Split the alkene in half perpendicular to the pi bond. On each side, apply priorities using the SIP rules. We do not rank all 4 groups together. We rank the 2 groups on the left separate from the 2 groups on the right. Just like with R&S stereochemistry, the highest atomic number wins. If those group tie, we go out to the next level. This is priority 1, the methyl group is priority 2. Separately, on the other side of the alkene, the aldehyde is priority 1, and the implied hydrogen is priority 2. Then, split the alkene in half again, parallel to the alkene. By drawing an imaginary equator right through the center of the alkene, we can check to see if the 2 highest priority groups are together in the same hemisphere of the molecule or on opposite sides of the equator in different hemispheres of the molecule. We look at only the highest priority groups on each of the carbons. These 2 groups are together in the same hemisphere of the molecule. This alkene is a Z isomer. Let's work through a few more quick examples to hammer the point home. First, split the alkene perpendicular through the alkene and assign priority labels to each carbon separately. Carbon beats hydrogen on the left, carbon also beats hydrogen on the right. Draw a line parallel through the alkene like an equator. These highest priority groups are opposite the equator in different hemispheres. This alkene is an E alkene. Alkene drawn vertically? Who cares? Orientation doesn't matter. The rules are the same. Split the molecule perpendicular to the alkene. Prioritize the groups on each side of the alkene separately. On the top carbon, the carbon chain is priority 1, and on the bottom carbon, the carbon chain is also priority number 1. Draw a line parallel through the alkene like an equator. These 2 number 1 groups are together in the same hemisphere of the molecule. This alkene is a Z alkene. In this last example, when we split the alkene perpendicular to the alkene, we see that the carbon on the right is attached to 2 identical hydrogen atoms. Just like R and S stereocenters, if there are 2 identical groups attached to the same carbon, this falls outside the scope of E and Z, and this alkene does not get an E or a Z label. Just like a carbon with 2 hydrogens attached is not a stereocenter and doesn't get R or S, an alkene with 2 identical groups attached to the same carbon cannot be assigned E or Z. There's no higher priority, so there's no way to tell if it's in the same or opposite hemisphere. This last example illustrates an important point. When students try to assign E and Z labels based on the feel of the molecule, they'll often guess wrong. Take a second on your own, pause the video, see if you can assign this molecule an E or a Z label. First, we'll split the alkene perpendicular to the alkene. No issues on the left side of the molecule. Carbon beats hydrogen, but be careful on the right side of the molecule. It's not the overall coolness of the group, it's atomic number. And fluorine has a higher atomic number than this carbon. Fluorine is the higher priority over the benzene ring. Then, when we split the alkene parallel through the alkene to make the equator, we see the 2 number 1 groups are on opposite sides of the equator. That makes this an E alkene. We do not assign E and Z to alkanes or alkynes, not even cyclic alkanes where before we used cis or trans labels. We only use E and Z on alkenes, and only when each carbon has 2 unique groups attached to it. Don't try and assign 4 priority labels to the 4 groups around the alkene. Don't rank groups by the overall coolness of the group. Instead, always think priorities first. If this felt more structured than what you've seen before, that's the point. The E and Z system is finite, not tricky. Your next step is practice. Lots and lots and lots of practice. Pencil to paper. Slow, clean, and methodical. And if R and S still feel shaky, jump over to the R and S video, where I'll teach you a 3-step foolproof plan for assigning R and S to any stereocenter in the molecule. You're making real progress. I'm proud of you, ninjas.
Thanks for joining us today, ninjas. Be sure to watch these other videos to level up your ninja training even more. As always, don't forget to like and subscribe.